we already have a very successful theory of gravity, and that's general relativity. So how does entropic gravity compare, maybe as far as its predictive power is concerned, to general relativity?
Well, general relativity is a very successful theory. It has indeed predicted lots of things. I mean, about starting with the perihelion shift of Mercury, bending of light, black holes, they exist, gravitational waves. Even the fact that our universe is dynamical can be understood in general relativity. It's a theory that's already more than a century old. I mean, so there's some way that eventually we're going to replace it with something new because it doesn't combine very well with quantum mechanics. So entropic gravity is something that we are, well, how should I say, it's a proposal that is sort of in the first step. And we're not there that we have a final theory there. And I also would like to connect it to everything that's happening in our field more broadly. These ideas about entanglement, for instance, they have been proposed also by other people, I think notably by Mark van Raamstonk. Lenny Susskind has done important work in these directions, and Maldacena, of course. And so the whole idea of connecting quantum information, for instance, to gravity, I would sort of put together in my way of thinking about entropic gravity or emergent gravity. And that, I think, approaches the problem of what is cosmology and how we should think about space-time in a very different way than general relativity. So I hope that this new way of thinking about it can answer questions that general relativity cannot. And so there are problems that we'd like to sort of, well, understand better. I mean, one of them is this mysterious dark energy that we are observing in our universe. We don't have even an explanation yet in string theory, for instance, of how to describe a universe with dark energy in it. And this is also where I feel that the whole subject of emergent gravity needs to be understood better. I mean, we know quite well now how to derive Einstein's equations in this other universe that has negative curvature. It's called anti-de Sitter space, if to mention a name. But our universe has a positive energy and a positive curvature, and would be called de Sitter space if you think about it. That's the opposite of anti-de Sitter space. And certain things might be different. One of the things that's different in this universe we live in is that because it's expanding, things are moving away from us, and they're moving even faster when they're further away. So there's a certain distance where things are starting to move away from our Earth and our galaxy by more than the speed of light. And that means that we cannot send signals anymore and they disappear from our view. It's basically, we have again a horizon. We call this the cosmological horizon. So our universe, very much like a black hole, has a horizon, and that horizon also has an entropy and a temperature just like black holes have. So that is what makes an expanding universe different from the universe that was used in string theory in this holographic correspondence. So we should be able to now take what we learned from string theory and from this holographic ideas and put that in the real universe. And there I think that the whole ideas about emergent gravity may still work, but the implications might be different. And especially the questions about what is dark energy and what we're observing in galaxies and so on might be coming in a different light.
I'd like to come back to dark energy in a moment, but return to where we began. And you mentioned some of the accomplishments of general relativity. So Mercury, or explaining Mercury's perihelion, predicting gravitational lensing, gravitational waves, and so on. How has entropic gravity compared, or does it account for these things that general relativity already accounts for?
Yes, that should be in there. I mean, so general relativity differs from Newton's theory when the gravitational fields become very strong. So what I worked on is actually indeed a proposal for how emergent gravity would work in a universe with dark energy in it. And then you will find that when you take into account that there is this horizon, that there might be deviations from general relativity when the gravitational field is very weak. And that happens, for instance, in galaxies. If we look at galaxies, they also rotate very much like the solar system does. And just like the planets are moving around the sun, the stars are moving around the center of this galaxy. But the speeds by which they do this don't follow the pattern that we would have expected by Newtonian or Einstein's laws. They're going actually much faster. And the way that people try to explain this now is by assuming that there's much more matter there than we are observing. This is called the dark matter. And so what I propose is that there's some other way of explaining this that comes from, well, thinking about gravity as an emergent force, where it even connects to what happens in our universe, that we have this horizon and its associated temperature. So I indeed wrote down equations that kind of describe this. Actually, it connects to also other ideas that have been proposed by particular Milgram, who proposed a modification of Newtonian laws that can be compared also to experiments. So there are experiments we can do, observations, I should say, of galaxies that allow us to test, these laws. But I have to add here that I don't think that we have found the full derivation or the full understanding of these laws yet in generality. So I think it's a little early to say that we can already make very specific predictions that need to be tested. But at least the general idea, and there are some laws that we can test. For instance, for galaxies, we have indeed made some predictions for what happens when you go even further out, outside of where the stars are no longer visible. And I have a colleague, an astronomer in Groningen, who has done measurements together with students from here, and actually a postdoc, Margot Bauer, who has done observations that indeed verify this predicted behavior. I wouldn't call this yet a full proof of a theory, because, as I said, the theory is still in development, and but it's at least indicative of what is possible. And so when the theory is further along, we might actually have observational predictions to make that can be tested with observations in our cosmos.
One of the criticisms of string theory that you hear all the time is that it's unfalsifiable, in the sense that every time it runs into a problem, like it predicts the mass of some particle to be many orders of magnitude larger than measurements indicate it is, then the theorists just rejigger the theory and make it work. And so in this sense, it's unfalsifiable. But that criticism has never made much sense to me, because of course, if you're developing a theory, it is highly unlikely that the final theory is just going to fall right into your lap. I don't think that happens very often. It is an iterative process. So is that generally how you feel about entropic gravity at this point? If there is a prediction that doesn't pan out, or some observation doesn't match or mesh with theory, that just means that the theory needs to be iterated. It doesn't mean that it's wrong, because you have faith that the intuition is correct.
Yes, I think for string theory, of course, there were two phases actually maybe of the theory. One where it tried to make predictions about elementary particles and their forces. But the other one where we sort of now in is where we think more about the gravitational side of things, and indeed about black holes and white horizons, and eventually cosmology. that theory is not fully developed yet, but I feel that side of it can make predictions. But as you say, we're not at that stage yet. And so when people say, well, we're going to falsify entropic gravity or emergent gravity or even string theory at that level, I think they are running ahead of the game, because we have not made our theory is not finished yet. And also, this whole information paradox that sort of came out of Hawking's puzzle of black holes, I mean, the Hawking radiation and so on, eventually will lead us to understand gravity better and quantum mechanics. And once we do that, I believe we can make predictions that can be falsified. So I do think that string theory eventually, in the way at least I think about it, produces a falsifiable theory, precisely in the area of cosmology or understanding what the early universe was about. And that's where the biggest questions still are, and this is where we try to find answers.